Welcome to Lecture 2, an introduction to using quantitative data in evidence-based policy research. The introduction established the why transformative reform is urgent, why public opinion is not the fixed constraint it appears, and why positivist, quantitative methods are the appropriate tools for building the evidence that can move policy. This lecture begins to examine the how. Lecture 2 is the methodological foundation for everything that follows. It introduces the concepts, research questions, prediction, explanation, inference, causal claims, significance, effect sizes, and the communication of findings that you will use in every subsequent lecture. Take time with it. The conceptual clarity you develop here will determine how well you understand everything in lectures 3 through 9. The single most important boundary this lecture draws is between knowing that two things are associated and knowing that one causes the other. That distinction is the most consequential in quantitative social science, and by the end of the lecture, you will understand why it matters so much for policy. We open with the foundations of data-driven research, then establish the epistemological position, positivism, that underpins the whole course. We move through the machinery of inference and uncertainty, which is how we express honesty about what our data can and cannot tell us. We then work through the three main study designs in order of their capacity to support causal claims: observational, experimental, and quasi-experimental. The second half of the lecture addresses statistical significance and why it is not the whole story, before closing with a section on communicating findings, which is treated here as a methodological commitment, not an afterthought. Two things distinguish this lecture from equivalent content in most methods textbooks. First, our commitment to positivism is explicit and argued, not hedged. Second, the examples are grounded in real UK policy research. Food banks, flu vaccines, the 2022-23 cost of living crisis, rather than abstract illustrations. By the end, you should be able to identify research designs and their limitations in papers and briefings you read, and to articulate why those distinctions matter for the policy conclusions that can be drawn. We need to open with three imperatives that frame evidence-based policy research: identify, use, and communicate. These sound obvious, but each is a site of real failure in practice, and understanding what each requires is the first step toward avoiding those failures. On identification, the UK has excellent existing data infrastructure. The census aims to count every person in the country. The Labour Force Survey provides quarterly data on employment, unemployment, and economic inactivity for approximately 100,000 households. Understanding Society follows around 40,000 households annually, tracking health, income, employment, and social attitudes over time. These datasets are systematically collected, quality assured, and publicly available. You do not need to collect your own data to do serious policy research. The access routes matter practically. The UK Data Service is the gateway for academic researchers to access a wide range of official and survey datasets. Office for National Statistics, ONS, and NOMIS provide direct access to published statistics. The ONS is the UK's national statistics agency, responsible for producing official data on the economy, population, and society. For data that is not publicly available, administrative records, locally held datasets, freedom of information requests, and data partnership agreements are the routes. Before using any dataset, review its licensing terms carefully. UK General Data Protection Regulation, GDPR, and the Data Protection Act 2018 impose real legal obligations on researchers working with personal data. GDPR is the EU data protection law incorporated into UK law as UK GDPR, following Brexit, imposing obligations on all organisations that collect or process personal data. On communication, the obligation to communicate clearly is as much a methodological commitment as the obligation to use the right model. A finding that cannot be understood and used by the people who make decisions is not a contribution to evidence-based policymaking. We return to this at the end of the lecture and again in Lecture 9. We need to be direct about epistemology. We are positivists. There is a reality independent of human consciousness. Humans are subject to the same laws of nature as other animal species. Predictions can be made on this basis. This is not a philosophical indulgence. It is the foundation of everything that follows. The point about policy making is cutting. Every policy involves a prediction about how it will affect human beings. The question is not whether policymakers are making predictions, but whether those predictions are grounded in evidence or driven by ideology. Neoliberal reform is shaped by a deontological commitment to reducing government involvement in people's lives and makes a series of assumptions about the social impact of inequality that are evidence-free. That is also policymaking. It is just policymaking without an honest empirical foundation. Prediction as an analytical purpose is about forecasting. How many primary school places will be needed in 2030? What would the public finances look like under a basic income? Predictive models are evaluated by how accurately they forecast outcomes on new data. Simple linear regression is excellent for policy forecasting because it is transparent and interpretable. You can explain exactly why it produces the result it does, which matters when decisions must be justified to ministers, select committees, and the public. Machine learning, ML, models can be more accurate in some contexts, but their opacity is a genuine problem in high-stakes policy decisions. ML is a branch of artificial intelligence in which algorithms learn patterns from data to make predictions or decisions, often at the cost of interpretability. Explanation is different in kind. Here you want to know why something happens, which requires a theory and a testable hypothesis. Consider a class size example. We theorize that smaller classes improve outcomes because teachers can give more individual attention. We derive the hypothesis that students in classes of 20 or fewer will score higher, controlling for socioeconomic background. We test it. If the model supports the hypothesis, that is evidence for the theory, though not proof, since other theories might generate the same prediction. Inference is the process of using data from a sample to make claims about a population. We never have data on everyone. We always work with a subset of the people, households, or events we care about. The discipline of statistical inference is about being honest about that, quantifying how uncertain our estimates are so that policymakers can make appropriately calibrated decisions. The concept of a parameter is fundamental. A parameter is an underlying quantity in the world that we cannot observe directly. The true proportion of working households below the poverty line in the UK right now is a parameter. We cannot know it exactly. That would require complete data on every household. What we can do is observe a sample and calculate an estimator, our best available guess of the parameter based on the data we have. The counterfactual problem is what makes causal inference hard and important. We observe that a household is below the poverty line. What we cannot observe is what would have happened if circumstances had been different. If the household head had received a different level of education, or lived in a different region, or been born in a different year. Causal inference is the statistical attempt to approximate this counterfactual, to estimate not just what happened, but what would have happened under alternative conditions. The two sources of uncertainty of importance here are sampling uncertainty and model uncertainty. Sampling uncertainty is quantifiable. It shrinks as sample size increases, in a relationship related to the square root of sample size. Model uncertainty is harder to quantify and cannot be eliminated by increasing sample size. It reflects the possibility that we have not correctly identified all the confounders that might explain the observed relationship. This is why transparent reporting of which variables were controlled for, what assumptions were made, and what limitations remain is not optional. It is the scientific obligation. The standard error and the confidence interval are the two standard tools for communicating uncertainty in parameter estimates, and both appear throughout the literature you will read and in every output the models in later lectures produce. The standard error tells you how far off your estimate is likely to be, on average, from the true population value. It depends on two things: how variable the population is and how large your sample is. In a very large sample, the standard error becomes small. Your estimate is close to the truth. In a very small sample, it can be large. Your estimate could be far from the truth. The 95% confidence interval is derived from the standard error. It represents the range within which, if you were to repeat your study many times, drawing different samples from the same population, 95% of your estimates would fall. Note carefully what this does not mean. It does not mean there is a 95% probability that the true parameter lies within your specific interval. The true parameter is fixed. It is either inside or outside your interval. The probability refers to the procedure, not to the specific interval. The declining returns to sample size is practically important. Going from 50 to 100 participants reduces your standard error by about 29%. Going from 100 to 150 reduces it by only 18%. Going from 1,000 to 1,500 reduces it by only 18% of that smaller standard error. This means there comes a point where collecting more data is expensive, but produces only marginal improvements in precision. A genuine practical trade-off in research design that you will face when planning the surveys and sampling strategies in later lectures. It is worth watching the embedded YouTube video to examine confidence intervals further. Observational studies are the dominant form of research in social science and public policy, and they are also the form most prone to misinterpretation. Understanding what they can and cannot tell us is one of the most important practical skills in applied policy research. The fundamental limitation is this: in an observational study, you observe the values of variables as they naturally occur. You do not intervene to change anything. As a result, if you find an association between two variables, you cannot be certain which of the three possibilities on the slide explains it. This is not a statistical failure. It is a logical consequence of the study design. Cross-sectional studies measure everything at one point in time. They are the most common form of observational data and the most limited for causal inference. Longitudinal studies, which follow the same individuals over time, are better because people's fixed characteristics, genetics, childhood environment, personality, do not change between waves. They cannot explain why the same person's income and life satisfaction both changed in the same direction. But even longitudinal data cannot achieve the certainty of an experiment because something else might have changed alongside both variables. The predictor outcome mediator framework is important for research design and interpretation. A predictor is the variable you theorize as the cause. An outcome is what you theorize as being influenced. A mediator sits between them on the causal pathway. If you want to estimate the total effect of income on life satisfaction, you should not control for travel, because travel is part of the mechanism through which income operates. Controlling for a mediator when you want the total effect is a common and consequential analytic error. These two examples are worth dwelling on because they illustrate something fundamental about causal inference in policy-relevant contexts, and because both have direct implications for real policy decisions. The food bank example is particularly powerful. If you observe that people using food banks have worse health than people who do not, it would be a serious analytic error to conclude that food banks cause poor health. People who use food banks are experiencing poverty, housing insecurity, and chronic stress. Precisely the social determinants that are known, from extensive research including the Marmot reviews, to drive poor health outcomes. Food banks are a response to those conditions, not their cause. The policy implication is direct. A government that concluded food banks were causing poor health and closed them would not improve health outcomes. It would remove food from people who are already in poverty, making both food insecurity and health outcomes worse. The causal analysis leads to the opposite policy recommendation from the naive observational association. The flu vaccine example shows the same problem from a different angle. In observational data, vaccinated people have more flu. This seems to suggest the vaccine causes flu, exactly the wrong conclusion. The reason is that the people who seek vaccination are precisely those most at risk: the elderly, the immunocompromised, healthcare workers. They get vaccinated because they are high risk, and they are then formally diagnosed with flu at higher rates than the general population. Once you randomize assignment to vaccine versus placebo, controlling for this selection effect, the truth emerges. The vaccine reduces flu risk substantially. The observational data was pointing in exactly the wrong direction. This is why RCTs remain the gold standard for causal evidence, and why observational findings always need to be contextualized within broader knowledge of the causal mechanisms at play. The embedded YouTube video outlines why correlation does not equal causation. The randomized controlled trial is the gold standard for establishing causation, and the logic is worth stating precisely because it is the foundation for understanding why all other study designs are weaker. Random assignment to conditions, vaccine versus placebo, training program versus control, cash transfer versus no transfer, ensures that the two groups cannot differ systematically in any characteristic that might affect the outcome. This is the magic of randomization. It distributes all background characteristics, measured and unmeasured, equally across groups in expectation. So if the treatment group shows a different outcome from the control group, the only explanation that survives is the treatment itself. The practical limitation is real and important. We cannot randomize people into poverty, unemployment, bad housing, or most of the conditions that matter most for social policy. This is why most policy research relies on observational data and quasi-experimental designs. But where experiments are feasible, evaluating pilot programs, testing intervention designs, assessing specific welfare policies, they should be used. The Welsh Government's Basic Income Pilot for Care Leavers, mentioned in Lecture 7, is an example. The distinction between covariates and moderators is analytically important. Covariates are variables like age or sex that might affect the outcome, but are not the focus of the study. In a well-randomized experiment, you generally let the randomization balance these and do not adjust for them in the analysis. Doing so changes what you are estimating in subtle ways. But when your research question is specifically about whether the effect differs by some characteristic, whether basic income has different effects for men and women, or for different age groups, that characteristic becomes a moderator and must be included as an interaction with the treatment variable. The difference between a nuisance covariate and an effect modifier is the research question, not the variable itself. We cannot randomize people into unemployment or into a cost of living crisis. But sometimes the world creates variation that approximates randomization, and quasi-experimental designs exploit that variation to make stronger causal claims than a simple observational study can support. The core logic is to find a source of variation in the independent variable of interest, that is, for practical purposes, independent of the individual characteristics that might confound the relationship with the outcome. If a policy is rolled out in some regions but not others due to administrative timing rather than any characteristic of those regions, The regional variation in policy exposure approximates random assignment, as long as the regions are genuinely similar to each other in other relevant respects. The changing cost of living study is a particularly relevant example. Nettle and colleagues used the variation in how severely different households were exposed to energy price increases in 2022 to 23 to estimate the causal effect of financial pressure on mental and physical health outcomes. The 2022 to 23 cost of living crisis was not randomly assigned. Households with older, less efficient heating systems and lower incomes faced larger relative increases in their energy bills. But the study design carefully accounts for these pre-existing differences, using longitudinal data to track changes within the same households over time. The three quasi-experimental approaches listed in the bullets are the workhorses of applied policy evaluation. Difference in differences compares the change over time in the treated group against the change in an untreated comparison group. Regression discontinuity exploits the fact that policies often have sharp eligibility cutoffs. People just above and just below a threshold are very similar, so comparing them approximates random assignment. Instrumental variables use an external source of variation, something that affects the treatment but does not directly affect the outcome through any other channel, to isolate the causal effect of interest. Each has its own assumptions and limitations, and the researcher must provide evidence that those assumptions are plausibly met. Statistical significance and the p-value are probably the most misunderstood concepts in all of empirical social science. We address this directly, and the correction matters for how you read and produce evidence. To begin, we need to understand what a p-value means, the probability of observing data as extreme as we observed, given that the null hypothesis is true. Note what this does not mean. It is not the probability that the null hypothesis is true. It is not the probability that your result is real. It is not a measure of effect size. These misinterpretations are extremely common, including in published academic papers, and lead to real errors in what gets treated as reliable evidence. The null hypothesis is the default assumption. There is no effect, no difference, no association. Statistical testing asks whether the data provides sufficient evidence against this default to justify rejecting it. When p falls below the conventional threshold of 0.05, we say the result is statistically significant, meaning we reject the null hypothesis. But as we note, this threshold means that 1 in 20 tests will produce a significant result by chance alone, even when the null is true and no effect exists. In a complex dataset where many potential relationships might be tested, finding a few significant results is not surprising and is not strong evidence. The embedded YouTube video explains p-values in greater detail. The lecture's core message on significance is clear. Statistical significance tells you something about whether an effect exists. But for policy decisions, the relevant questions are about magnitude and direction. How large is the effect, and does it go in the right direction? These questions are answered by effect sizes and confidence intervals, not by p-values alone. The lecture makes 3 specific arguments for why effect sizes matter more than p-values for policy research, and all 3 are worth internalizing. First, p-values depend on sample size in a way that effect sizes do not. The FRS has around 25,000 households. With a sample that large, almost any association, even one of trivial magnitude, will be statistically significant. Conversely, in a small sample of 200 households, a genuinely important effect might not reach significance simply because there is too little data to estimate it precisely. Effect size is independent of sample size. What changes with larger samples is the precision of the estimate, not the size itself. Second, policy questions are intrinsically about magnitude and direction. When we ask whether a basic income scheme reduces poverty, the question is not whether it reduces poverty at all. It almost certainly does, at least by a trivial amount. The question is by how much, and whether that reduction is large enough to justify the fiscal cost. Only effect sizes answer that question. The example of a training program that increases employment by 0.5 percentage points makes this concrete, statistically significant, but potentially not worth the investment. Third, the confidence interval format is superior for policy communication. Saying, the effect is statistically significant with p equals 0.03 tells a policymaker almost nothing useful. Saying, the program increases employment by 12 percentage points with a 95% confidence interval from 8% to 16% tells them the most likely effect size, the range of plausible effects, and that even at the lower bound, the effect is meaningful. This is what policymakers need to make informed decisions about intervention costs and likely benefits. The multiple testing point is practically important for your own research. If you test 20 relationships in a dataset and find 2 that are significant at p equals 0.05, that is exactly what you would expect to find by chance, even if no real relationships exist. Pre-registration, specifying your hypotheses and analysis plan before seeing the data, is the gold standard protection against this. At minimum, always report how many tests you conducted and be explicit about which were pre-specified versus exploratory. This lecture treats communication as a methodological commitment, not an afterthought, and this position distinguishes it from most quantitative methods textbooks. The goal of evidence-based policymaking is not to produce sound research, it is to produce research that influences decisions. Those are different goals, and the second requires communication skills that the first does not. The point about visualization is straightforward, but worth emphasizing. What is obvious to a researcher who has spent months with a dataset is often completely opaque to a minister or civil servant encountering the findings for the first time in a 2-page briefing. Graphs, charts, and tables make complex data accessible, not by simplifying it, but by presenting it in a form that connects visual pattern recognition to the question being asked. The 3 properties of good visualizations are clarity, pattern recognition, and impact. Clarity means the chart can be understood without reading a paragraph of explanation. Pattern recognition means the visual form matches the analytic question. Trends over time belong in line graphs. Comparisons across groups belong in bar charts. Associations between continuous variables belong in scatter plots. Impact means that a well-designed chart is persuasive in a way that a table of numbers is not by distorting, but by making the evidence impossible to ignore. Displaying uncertainty is not optional. Confidence intervals and error bars are how you communicate honestly about what the data show. A point estimate without a confidence interval looks more precise than it is, and policymakers who act on a point, estimate without understanding the range of plausible values, may make poorly calibrated decisions. Honesty about limitations can actually increase confidence in the analysis. Audiences who see researchers acknowledging what they do not know are more likely to trust what they claim to know. This is a practical argument for intellectual honesty, not just a moral one. The title of this conclusion, Honest Evidence, is evidence with its limitations shown, is the most practically important idea in the lecture. The instinct to hide limitations and present findings as more certain than they are is understandable. Researchers fear that acknowledged uncertainty will be used to dismiss their work. The evidence suggests the opposite. Audiences, including policymakers, are more likely to trust and act on research that is transparent about what it does not know. That is not an argument about academic virtue. It is a practical argument about how evidence actually influences decisions. The first thread is positivism as the foundational commitment. This course takes a positivist position. There is a reality independent of human consciousness, and predictions about how policy will affect human beings can be made on the basis of evidence rather than ideology. This is not an uncontested philosophical position, but it is the one that makes quantitative policy analysis possible. Every method we encounter, microsimulation, health modelling, conjoint analysis, depends on the assumption that regularities in human behaviour can be measured, modelled, and used to predict policy effects. If you reject that assumption, you reject the project. If you accept it, the question is how to do it honestly. The second thread is the causal inference hierarchy. The distinction between observational, quasi-experimental, and experimental designs is a ranking from less to more able to isolate a causal effect. Observational studies identify associations and control for known confounders, but unmeasured confounders always remain possible. And the food bank and flu vaccine examples show that confounding can run in exactly the opposite direction to the true causal effect. Quasi-experimental designs exploit naturally occurring variation. RCTs eliminate confounding through random assignment and are the gold standard when feasible. Most policy-relevant questions cannot be answered with RCTs. That is not a reason to abandon causal thinking, but a reason to be precise about what your design allows you to claim. The third thread is the counterfactual. People who use food banks have worse health outcomes than those who do not, but the correct interpretation is not that food banks harm health. Food bank users face poverty, housing insecurity, and chronic stress. The actual causal drivers of poor health. Food banks are a response to those conditions, not a cause. The counterfactual question, what would happen in the absence of this intervention, yields the opposite conclusion to the naive association. Every time you encounter an observational association, ask first, what is the counterfactual? The fourth thread is the practical meaning of statistical significance. The p-value tells you the probability of observing data this extreme if the null hypothesis were true. It does not tell you the magnitude of the effect. In a large enough sample, a program that increases employment by half a percentage point will produce p less than 0.05, statistically significant and policy irrelevant simultaneously. The confidence interval is the right tool. It conveys the likely size of the effect and the uncertainty around it together. Pre-registration addresses the multiple testing problem. Reporting all tests conducted, not just significant ones, is the minimum standard of honest evidence. The fifth thread is communication as an analytical task. Getting the technical analysis right is necessary but not sufficient. Research influences policy when it reaches the right people in the right format at the right time. The confidence interval is not optional. It allows readers to make an honest assessment of the evidence. Acknowledging limitations in a briefing distinguishes a credible analyst from an advocate. The most dangerous form of policy evidence is not the study with large uncertainty intervals honestly displayed, but the study with artificially small intervals produced by ignoring the hardest to quantify sources of uncertainty. Lecture 3 applies these principles to the datasets the course depends on: the Family Resources Survey, the Living Costs and Food Survey, the Wealth and Asset Survey, and Understanding Society. The methods covered, representative sampling, stratified design, grossing up, confidence intervals, transparent reporting of limitations, are the foundational practices that make those datasets usable for policy analysis. Understanding why grossing factors exist, what confidence intervals mean, and why underreporting of alcohol and tobacco in the LCF is a research design problem rather than a data entry error. These are not incidental details. They are the difference between generating credible evidence and producing numbers that merely look like evidence.